Good morning, everyone. I am Dr. Hisham Mohammed, and I am pleased to present this work together with Zabirul Islam, Motaleb Hossein Manik, and Professor Zay Wang. Our project is titled AI for BME Education, a case study on BMED 2300. In this work, we explore how artificial intelligence can support biomedical engineering education. This project is conducted in the Department of Biomedical Engineering at Rensselaer Polytechnic Institute. Today, we will share the motivation behind the project, the system design, the case study setup, and the key insights from our work. BMED 2300 is a sophomore level course that introduces biomedical engineering students to instrumentation and medical imaging. The course first builds a technical foundation in measurement systems, signals and systems, circuits, sensors, Fourier analysis, sampling, and filtering. Students then apply these foundations to major imaging modalities, including X-ray Connecticut, PET and SPECT, MRI, ultrasound, and optical imaging. So, the course is not only about learning different imaging modalities. It helps students understand how physical signals are generated, measured, processed, and converted into biomedical images. The course uses two main textbooks. The instrumentation portion uses Bioinstrumentation by John Webster, while the imaging portion uses Introduction to Biomedical Imaging by Andrew Webb. Although the course is mainly lecture-based, it is complemented by 3 hands-on MATLAB sessions. These sessions help students explore convolution, Fourier transforms, and CT image reconstruction using the radon transform. This hands-on component is important because students can see how mathematical concepts become computational imaging operations. For example, when students perform a two-dimensional Fourier transform and separate phase and amplitude information, they begin to understand how image structure is represented in frequency space. The course learning outcomes focus on helping students understand the operating principles and characteristics of major clinical imaging modalities, including X-ray, Connecticut, nuclear imaging, MRI, ultrasound, and optical imaging. Students also learn about image quality, diagnostic performance, and basic performance metrics of imaging systems. This wording is more appropriate than saying students estimate diagnostic accuracy, because the course introduces these ideas at a sophomore level. Students also practice Fourier transforms and other signal and image processing tasks using MATLAB. Together, these outcomes prepare students to understand imaging systems as engineered systems built from physics, instrumentation, computation, and signal processing. One major challenge in BMED 2300 is that students encounter many new concepts at the same time. The foundation part includes measurement systems, signals and systems, circuits, operational amplifiers, sensors, convolution, Fourier transforms, sampling, and filtering. Many sophomore students have not seen these topics in this applied biomedical context before. The imaging part adds another layer of complexity. Students need to understand signal generation, interaction with the human body, detection, imaging algorithms, instrumentation, contrast, image quality, diagnostic performance, and safety. Because of this, students often need support that is more targeted than general online information. They need help connected to the exact lecture, the exact slide, and the exact moment where confusion occurs. These challenges motivated us to ask whether an AI system could provide timely, lecture specific help without taking students away from the learning context. That is the motivation for ALI.
Now we introduce a live avatar lecture interactive video engine. The main idea is to move beyond passive lecture videos. Instead of only watching a recording, students can pause the lecture when they are confused, ask a question using text or voice, and receive an answer grounded in the course lecture content. This is especially useful in medical imaging, which is a technically demanding domain. Concepts such as ring artifacts, Fourier reconstruction, Hounsfield units, and modality-specific physics require precise context-aware explanations. In our current implementation, Alive has been deployed for 23 lectures in BMED 2300 at RPI. The deployed student-facing question and answering backend runs on institution-controlled GPU hardware, including H100 GPUs. The code retrieval, LLM inference, and student interaction data remain within the institutional environment. The goal is not to replace the instructor. The goal is to extend the instructor's presence and provide students with timely support when they need it. Let's look at the learning problem from a student's point of view. Imagine a student watching a city reconstruction lecture. Around the middle of the lecture, the student becomes confused and asks, why does a ring artifact appear in city reconstruction? Without Alive, the student has limited options. They can pause the video, search online, open a textbook, or wait until later to ask the instructor. But each option interrupts the learning flow. Search results may be too generic. A textbook explanation may be correct, but it may not match the exact slide or the instructor's explanation. If the student continues watching while confused, that misunderstanding may affect later topics such as artifact correction, image quality, and diagnostic interpretation. Many online learning environments also struggle with limited timely feedback. So the problem is not only access to content, but access to contextual help at the moment of confusion. With Alive, the student can pause the lecture and ask the question immediately. The system uses the lecture context and pause timestamp to retrieve relevant material and generate a short, grounded answer. The key benefit is that the student stays inside the lecture environment. The confusion can be addressed immediately while the learning moment is still active. A natural question is, why not just use ChatGPT, Google, or a generic AI tutor? There are three main limitations. First, general purpose tools do not automatically know the lecture context. They do not know which slide the student is watching, what timestamp triggered the question, or how the instructor explained the topic. So even when an answer is generally correct, it may not align with the specific lecture. A better way to describe this is not 0% contextual grounding, because a user could manually provide context to a general LLM. The more accurate point is there is no automatic lecture or timestamp grounding in off-the-shelf use. Second, medical imaging requires technical precision. In our test set, the base Llama-3.1-8b model showed a 5.9% factual error rate, while the Alive fine-tuned model reduced this to 1.0%. This makes the claim specific to our evaluation rather than making a broad claim about all base LLMs. Third, there are privacy and governance concerns. Student questions, lecture materials, and interaction data should be handled carefully in university-administered courses. So Alive is not simply another chatbot. It is lecture-aware, domain-adapted, and designed to preserve the educational context. This slide shows the overall system architecture. There are three main parts. The first part is offline lecture preparation. A raw lecture video is transcribed using Whisper ASR, and the transcript is refined for clarity. The lecture is then converted into a prepared avatar-delivered version. In this workflow, Synthesia is used for prepared avatar lectures. At the same time, the lecture content is split into slide-aligned chunks and indexed for retrieval. The second part is the student interface. Students watch the avatar-delivered lecture. When they pause the lecture, a Quanda window appears. They can ask a question by typing or using voice input. The third part is the backend. The system retrieves relevant slide-aligned lecture chunks using FACE, then sends the retrieved context to a domain-adapted Llama-3.1-8b model running with LoRa and VLM. The answer is generated on institutional GPU hardware. For avatar response generation, MuseTalk supports the real-time talking head avatar component. This is different from Synthesia, which is used for prepared avatar lecture production. Let's do a quick recap of how Alayev works. Step 1. The student pauses the avatar delivered lecture at the moment of confusion. Step 2. The student asks a question either by typing or using voice input. Step 3. The system retrieves relevant lecture content. Retrieval is not based only on text similarity. It also uses the pause timestamp to prioritize lecture segments near the student's current learning moment. Step 4. The domain-adapted LLM generates a concise answer, usually 2 to 3 sentences. This is important because the answer needs to support real-time learning, not become a long textbook-style explanation. Step 5. If avatar mode is selected, the answer is converted into speech and rendered through the talking head avatar pipeline. The temporal retrieval term is designed to favor lecture segments near the pause timestamp, so the answer is grounded not only in the question but also in the student's current lecture context. This slide summarizes the main quantitative results. First, timestamp-aware retrieval improved retrieval accuracy. NDCG at 1 increased from 0.30 to 0.64, which is a 113% improvement. This means the most relevant lecture segment was much more likely to appear at the top of the retrieval results. Second, the fine-tuned Alive model produced shorter and more direct answers, reducing average LLM generation time from 1.59 seconds to 0.60 seconds. This is important because Alive is designed for real-time use during a lecture pause. Third, answer quality improved. The fine-tuned model improved BERT score and root scores, and the factual error rate dropped from 5.9% to 1.0% on the test set. Fourth, avatar synthesis takes about 1.85 seconds, which makes avatar-based responses practical during a pause interaction. Overall, these results suggest that Alive can provide faster, more grounded, and more course-specific support than the baseline model in this evaluation. This slide is important because Alive is not only a prototype, it has been deployed in a real course setting. The system is currently used for BMED 2300, bioimaging, and bioinstrumentation at RPI. We processed and deployed 23 lectures from the course. The front end is hosted through GitHub pages, and the backend is connected through a secure HTTPS tunnel. The heavy computation, including retrieval and LLM inference, runs on RPI GPU servers. A short demo video is also available showing how a student can pause the lecture, ask a question, receive a grounded answer, and continue learning without leaving the lecture environment. Here is the demo.
Welcome back. We can see today's topic is CT reconstruction.
Ring artifacts appear due to the edge overlaps created by the wrapping around effect in circular convolution, which can be mitigated by using zero padding before performing the convolution.
To evaluate Alive, we will measure more than whether students like the system or not. The planned study uses a within-subject, counterbalanced Latin square design. In the Alive condition, students watch the lecture and complete at least 3 question and answering interactions. The study targets 40 participants with a minimum of 30 participants, including RPI, undergraduate, and graduate students who have not previously taken the medical imaging course. The study protocol is being handled through the IRB process before student enrollment. We will measure several dimensions. First, usability and performance, ease of use, response speed, usage frequency, and preference for text or voice input. Second, learning outcomes, concept understanding, homework support, exam preparation, retention, and cross-topic connections. Third, trust and critical thinking, whether students trust Alive appropriately, verify answers using slides or textbooks, and identify incomplete or incorrect responses. Fourth, human interaction and over-reliance, whether Alive supports learning without replacing class attendance, office hours, instructor interaction, or peer discussion. Finally, skill development and academic integrity, whether students use Alive as a learning aid rather than as a shortcut for submitted work. Our next step is to add multimodal retrieval so Alive can index slide images, diagrams, equations, and figures. We will explore multimodal large language models for joint visual textual understanding of educational materials. We will add streaming to reduce time to first token and make responses feel more immediate. Finally, we will scale the system to other courses and instructors.
As you can see, our students are outstanding. They even created avatars of us to teach our courses. So perhaps we can safely retire. Oh, just kidding. The pedagogical innovation is a strong tradition on our campus, and we have an excellent track record, as shown in the references on this slide. As early as 2020, we innovated our medical imaging course within a deep learning framework. So, as another example, last year we published a paper on a fine-tuned ChatGPT app as a teaching assistant for our medical imaging course. The local faculty members involved included doctors Kruger, Ha, and Yang, as well as Mohammed and myself. Here are additional references from us. The Alive pipeline that Zabi presented is among the most recent papers in this line of work, which has attracted attention outside RPI. For example, University of Alabama at Birmingham researchers are collaborating with us to utilize Alive for pedagogical research. A few weeks ago, Pincon suggested trying a dual instructor presentation mode. We hope this will make the delivery of the teaching materials more engaging. There are many other interesting ideas to try in this domain that here is a demo of our podcast. So welcome back, everyone. I'm Dr. Dewan, and joining me as always, Dr. Hisham. Today, we begin ultrasound imaging part 1, and I'll say right away, if I had to choose one modality that surprises students the most, it would probably be ultrasound.
I agree. Welcome, everyone. The surprise comes early because if you followed the course so far, you've seen a pattern. X ray, nuclear imaging, MRI, all of them are built around electromagnetic waves. But then we arrive at ultrasound, and suddenly that whole framework changes.
And now, let me offer a few thoughts on our vision for the future of education. In the top left, you can see the logo commemorating RPI's 200th anniversary, where 200 is stylized as to infinity. That infinity symbol resembles the logo of Meta, leading to the concept of the metaverse. In 2022, we published our perspective on the healthcare metaverse. In parallel, here we envision an education metaverse. In a recent internet survey, I found 6 types 3D display technologies. Looking ahead, avatars may take on fully three-dimensional forms for both students and instructors, and immersive environments may redefine virtual and mixed reality in education. Please note that the interactive avatar presented by Zabi is still based on a student-led initiative. As a next step, we can make the interaction bidirectional, allowing the avatarized instructor to proactively ask students questions based on their academic records, facial expressions, gaze, pauses, and other cues, as well as their responses to real-time questioning. Just as precision medicine tailors care to the individual, we envision that future AI-based education will be personalized and optimized for each student in a highly proactive yet very friendly fashion. In this way, every student will have access to a dedicated high-quality instructor 24 hours a day, 7 days a week. We have greatly enjoyed innovating educational practice with strong departmental and institutional support. The School of Engineering and the School of Business generously covered the licensing fee of several $1,000s, enabling us to create avatars and animate our lectures. Special thanks go to Dean Dr. Shekhar Garg. This work is a part of the BME AI for Education initiative. We hope to continue developing new techniques and achieving even better results in the future. Thank you for your attention. We welcome your questions and potential collaboration.